Good evening. This lesson is on refraction and lenses. This is the third lesson in the Electromagnetic Radiation and Optics module. The first thing we're going to talk about is refraction. So when light passes a boundary or medium and changes speed, it is called refraction. The change of speed or direction depends on the index of refraction of the two media that the light passes through. The index of refraction is the relation of the speed of light in a vacuum to the speed in a given material. So there are some examples of different materials in the index of refraction. You don't have to memorize these. They will be given to you in a problem if needed. We actually will be measuring the angles in the two different mediums when diffraction occurs. The first example is when an angle of refraction is the smaller angle, then the ray of incident when an angle goes into a more dense medium. So if we look at the example below, this angle is going to be smaller than this angle. So this means that this material that we see in the blue is going to be more dense. Mathematically, the equation for Snell's law is what you see on your screen right here. And it doesn't matter which angle is which as long as you are consistent, so make sure you follow that. And then also double check to make sure your calculator is in degrees and not radians. The critical angle is the minimum angle where a photon leaving medium will reflect instead of refract. This only can occur when a ray is leaving a medium and going to a medium with a smaller index of refraction value. So remember, at angles greater than the critical angle, the ray follows the law of reflection, which is what we have been talking about earlier in the module. Here are some of the equations that you'll see, and it looks like my, the copy of it did not go well, so I'll make sure to explain these equations when we get to the practice problems. I'm sorry, one more thing. They are the same equations that you did during the practice problems for mirrors, so these should not be new to you. The images of the far side of a positive and near side are negative. The focal length for a converging lens is positive and negative for a diverging lens. The object distance is positive, and the image distance is positive if it is on the opposite side of the lens from the object, and negative if it's on the same lens side as an object. So another way to think about it, which I think is a lot more easier, is that divergent, we are talking about the same kind of concepts as convex, and then convergent will be the same kind of concepts as concave. Assume that every lens in this course is a thin lens, which means any lens that has a thickness considerably smaller than the diameter of the lens. Rays will travel through a lens instead of bouncing off like a mirror. So here's an example of a converging lens. So this is going to bring rays of light together. So right here on the left side, we have the near focal point, and then we have over here on the right side, the far focal point. And this O is going to be the center of the lens, and if light passes right in the center of the lens, which is represented by the O, it's going to travel in a straight line. So here are the three rules with a converging lens. First of all, you're going to do a ray parallel to the principal axis refracts through the far focal point. So that's going to be the blue line down here. So we see a line, and it's going to refract or bend and travel through that far focal point. And then a ray passes through the near focal point is going to refract parallel. So if we have a ray going through the near focal point, after it crosses the lens, it's going to go parallel. And when those two intersect, that's where the image is going to be formed. If the object is placed between the optical center and the near focal point, please follow these directions. A lot of students were getting points off during the lab for this. So if the object, again, is in between the focal point and the lens, what you're going to have to do is follow the same rules. So one passing through the focal point, or the far focal point. The other one would reflect parallel as soon as it crosses the lens. And again, extend this line to go through that focal point. So where these two intersect, if we extend those two lines, it's going to be on the same side of where the object is. So it's same as the concave mirror concept. So here are the rules for a diverging lens. A line parallel to the principal axis refracts away from the near focal point. Same concept with the blue line here. A ray headed towards the far focal point refracts parallel, so we see the green line down here. So you're going to extend the lines to get an imaginary intersection. So this is the intersection where you see that small arrow. And it's always going to be a reduced virtual image smaller than the object. So it's going to be the same rules as the mirrors that we were discussing earlier in the first lesson. All right, so here are several practice problems that we're going to walk through. The first one says the index of refraction for a medium where light travels at 2.5 times 10 to the 8th meters per second. So we're going to use this formula right here. Plug in what we know. Again, this is the constant number of how fast light travels. This is the median where it was given to us in the problem. So all we do is divide those two numbers and we should get 1.20. The speed of light in sapphire, so it has to be given us that index. So it's 1.77, so we're just going to rewrite it. Again, use the speed of light divided by the index, and we should get 1.69 times 10 to the 8th meters per second. The angle of refraction of a ray of light traveling in water, again, they give you the index right there of water, 1.33, that strikes the boundary at an angle of 37.2 degrees and transitions to air. They give it the second index of 1.00. I thought I called all these, but I didn't. Remember those Q's or that theta or that angle symbol in all of these equations. Make sure you have that correct in your notes. But what we're going to do is plug in the index, 1.33 of that water, times the sine of the angle, 37.2, and divided by the index of the air, 1. So we should get 0.804. So then we need to take the inverse sign to get the actual angle. And if we plug that into our calculator, make sure your calculator is set on the correct settings, you should get 53.5 degrees. Letter D says, what is the index of refraction for a substance if a ray of light leaving quartz, there's the index, at an angle of 25.3 degrees has an angle of 15.9 degrees in the new substance? So again, we use that same equation, and again, the Q's are the thetas. I don't know why it does that. So make sure, again, you have that in your notes. We plug in the index of quartz, 1.46, sine the angle, 25.3, divided by the sine of the angle, 15.9. And this time we're looking for that index of 2.28. And remember, the index of refraction does not have a unit. Here's a second practice problem. This one is talking about a critical angle for a ray leaving sapphire, which is the index of 1.77, is 59.8 degrees. What is the index of refraction of the medium that the ray is traveling to pass into? So we're going to take the sine theta of the quartz, rewrite the formula to solve for that first refraction, and what we're going to plug in is 1.77, which is that index, sine 59.8, and so we should get 1.53. Again, no units because we're asking for the index of refraction. All right, lots more. Letter A, the practice problem says calculate the following for a converging lens with a focal length of 6.50 centimeters and an object that is 8.20 centimeters tall. Letter A says, what is the location of the image if the object is placed 10.50 centimeters from the lens? We use that formula. This one was the one that was cut off earlier in the presentation. We plug in what we know, so 1 divided by 6.5 minus 1 divided by 10.5, and we should get 0.0586. We plug in that with the distance of the image, and we should get 17.1 centimeters. Now it's asking for what is the height of the image. So again, we use the magnification, that's the same formula that we use for the mirrors. We plug in what we know, negative 17.1, and it's negative because of the image location, times 8.2, which is the object height, divided by 10.5, and we should get negative 13.3 centimeters. This 10.5 comes from part A of the problem up here, if you were wondering where that came from. So now it's asking, is the image real or virtual? We know that it's real because the positive image distance, which would be from letter A. And this is what is the magnification of the image, so we use that magnification formula, which is right here. Height of the image divided by the objective height, the object height, and so we do negative 13.3 divided by 8.2, and we should get negative 1.62. Again, magnification is in half units also. Letter E is asking, is the image upside down or right side up? We know that it's upside down because it has a negative magnification. Letter F says the object is now moved so that it is 2.75 centimeters from the lens. What is the location of the image? So we do the same process that we did up in letter A, same formulas, except now we're going to be changing the distance of the image to 2.75, and so we should get negative 0.21. We plug that in to get the image location, and we will get negative 4.78 centimeters. Letter G says, what is the height of the image? So the same thing, 14.2 centimeters after you plug in the distance image as negative 4.78, which is right here. And letter H is the image real or virtual. It's going to be virtual because it has a negative image distance. And then it says, what is the magnification? Again, the same formula that we did earlier. 14.2 divided by 8.2 equals 1.73, so that means that it's going to be right side up because it has a positive magnification. All right, the last practice problem says calculate the following of the diverging lens with a focal length of 6.50 centimeters and an object that is 8.20 centimeters tall. So what is the location of the image and the object is placed 10.50 centimeters from the lens? Again, we're going to use the same formula that we did for the mirrors. Plug in what we know, 1 divided by negative 6.8. That's what's given up here, minus 1 divided by 10.5, which is given to us right here, and we should get negative 0.249. Then we plug that in to get the distance image, and we should get negative 4.01 centimeters. So what is the height of the image? And same concepts, just making sure our signs are correct. So negative 4.01 times 8.2 divided by 10.53, and we should get positive 3.14 centimeters. So that means that it is a virtual because it has a negative image distance. The magnification, we're going to use 3.14, which is what we calculated in letter B, divided by 8.2, which is given to us in the problem, the object height, equals 0.38. So we have a positive, which means that the image is right side up for that positive magnification. So you can see that all these problems are very similar to the mirror problems that we did in the first lesson of the module. Please let me know if you have any questions after you watch this recording.